Okay, so I want to look at a new rule for derivatives, and it's called the chain rule. And so to kind of get us to see the necessity of the chain rule and kind of see where it maybe comes from, I want us to look at this binomial here, 3x plus 1 squared. And it says which expression is the correct derivative. So take a second or two and think about, what do you think the correct derivative is? Now, maybe some of you thought, the derivative would have been 6x plus 2. Like maybe you multiplied the 2 down and said that's 3x plus 1. And then dropping the 2 to a 1, we get that. Distribute the 2, and you get 6x plus 2. So some of you maybe thought it was that equation right there. Okay, it's actually not that, and it's actually not that, and it's not that. If you're going to choose a wrong answer, that is the best wrong answer, but actually the right answer is this. So the question is why? Well, if instead of trying to do the derivative of this first, which if you did, then you would have gotten this answer, which is incorrect until you fix it using the chain rule. But if you would have expanded this first before you did the derivative, you would have gotten 9x squared plus 6x plus 1. And then the derivative of that expression, so f prime, equals 18x plus 6, which is this. Now, that 18x plus 6 is compared to like 6x plus 2. That 18x plus 6 is actually 3 times greater than 6x plus 2. And that's not a coincidence, okay? The fact that it's 3 times greater has everything to do with the fact that inside that set of parentheses is 3x plus 1. And guess what the derivative of 3x plus 1 is? Well, hopefully there is no guessing. You should know it. It's 3. Okay, and so that's the idea of this chain rule. A chain rule helps us deal with function composition. Okay, and function composition means that you have a function that's sitting inside some other function, right? So if I look here, technically I have a quadratic, right? 3x plus 1 squared. But like this quadratic is a function, but then there's another function inside that quadratic. It's the function 3x plus 1. That 3x plus 1 is sitting inside something that's being squared. And so when you have a function composition like f of g or f of g of x, something like that, each of the functions needs a turn at getting a derivative. And that's exactly what the chain rule is. And so if you look down below, hopefully I can, sorry. I apologize. I did not need to do that. Trying to get to my notes. Here we go. Scrolling down. Sorry. So that's exactly what this is right here. Like f of g of x. Like that's that composition. So I forgot. I didn't realize. Here's another question. What happens to the graph of sine of x when the coefficient when a coefficient is put in front of x? So example, like sine of 4x. So the idea there is that, if this were sine of x, right, remember it's our very aesthetically pleasing graph from 0 to 2 pi, sine of 4x means it's 4 times the frequency, or the wavelength is reduced by a factor of 4. So I'm going to get 4 sine functions within that graph. So it'll be like 1, 2, 3, 4. Okay, so in other words, it's going 4 times as fast, which means the derivative is going 4 times as fast, which means the slope is changing 4 times as fast, which means the function that measures it would have a factor of 4 in front of it. So, and again, that's just kind of trying to reiterate that you need to do derivatives of each of the components, because this 4x is a function embedded. So, back to this whole idea of a chain rule is that if you have a composition here, right, f of g of x, you need to find its derivative, then you have to do the derivative of the outer function first. I'll do f prime of g of x but then immediately after, I'm going to multiply by the derivative of g. And notice that you cannot change the identity within the derivative. You have to leave g of x alone. It's only when you get to the outside do you multiply by its derivative. Okay, and some helpful hints are look for grouping symbols, right? Grouping symbols. So look for things that are inside a square root, right? Because you could do square root of something. Look for something in parentheses because you could raise that to a power. Look for trig because it's like sine or cosine of something. Okay, so look for those grouping symbols because often within that group, there's another function and they each have to have a derivative. Okay, so let's take a look just at maybe example, like the examples here, 1, 2, 3, and 4 on this video. Let you kind of think about those, and then we'll do some more examples on the next video. Okay, so the first thing is find the derivative of sine of x squared. And here's the thing, I don't care what it's called. Like it could be sine of anything. Sine of anything. Like I think I always make a joke, like it could be sine of elephant. It doesn't really matter what's inside that. The derivative of sine of anything is cosine of that thing. So I have to address the outer function first. So the derivative, so the derivative of sine, so dy dx, the derivative of sine is cosine of that thing. So I don't really care what that thing is. That thing would go right there. So what was that thing? Oh, it's x squared. So I cannot change the identity. It has to be x squared. That does not get changed. I can't do the derivative yet. But then immediately after, and I always do in class a snap, immediately after, the derivative of x squared, which is 2x. This falls outside the function. That's separate from this x squared. Because remember, you can't change the identity of that. Like whatever was in here is right there. Then its derivative sits outside. Now, you might simplify that, and you might say, and then you might say that you could bring up the 2x in front just to avoid confusion. So it's 2x times cosine of x squared, but it's a separate function. That is separate than this in terms of the chain rule. Okay, all right. Let's look at the next one. Next function. Same concept that it does not matter what's inside. The derivative of cosine of black dot or elephant or anything is negative sine. So immediately I would go and say dy dx is equal to negative sine of that same thing. Cannot change the identity. It is matched. This goes there. So in other words, it's negative 5x. Sorry, it's 5x. 5x. Cannot change the identity. But then immediately after, you multiply by the derivative of 5x, which is 5. And you might pull that in front. So say dy dx is equal to negative 5 sine of 5x. And to kind of go back up to that first part of that example, the fact that there's a 5x here just in that function, if you were to graph that, that's increasing your frequency 5 times as great. So if the derivative changes, if the function is changing 5 times as quickly, then the function that measures the derivative values needs to also change 5 times as quickly. Okay, so next example. Coming down here, trying to grab that trying to grab the black dot. Black dot, there it is. Okay, so we have something raised to the 5th power. And the thing is, it doesn't really matter what that something is. The derivative of any 5th power function is 5 times that thing to the 4th power. We decrease it by 1. So now what was that thing? That goes here. So we don't want to change the identity of it. It's 4x minus 1. We can't do a derivative inside the parentheses. We must then do chain rule derivative outside. So then that's where that 4 comes from. It's the derivative of the inner function. I'd multiply the 5 and the 4 to get 20, and then leave it as 4x minus 1 to the 4th power. I mean, so much more efficient than thinking we'd have to like actually expand this using, the binomial expansion of the fifth power and then go ahead and group it up and factor it. I mean, that's so time consuming. Done by using chain rule. Okay. And then one more example, if I could grab that black dot, there it is. Okay. So one more example. Right now we've got 2 something cubed, and the derivative of 2 something cubed would be bringing the 3 down times that 2 something squared, right? So in other words, 6 something squared. And then you go back and say, well, what was that? I feel like a broken record. What was that something? Haha, that something was 6 minus x. So then that's what gets placed here. And you've got to check, what's the derivative of 6 minus x? Be careful, it's a sneaky chain rule. Its derivative is -1. So then the -1 comes in front times the original 6 that was there. So I could say that's 6 minus x quantity squared. Okay, so I liked the visualization of kind of covering up what that inner function is, because it kind of helps us and reminds us that don't change its identity. It has to be the exact same thing that's the embedded function in both. It's only afterwards then do you take the derivative, which would be the chain rule. Okay, so process that, think about those. We'll continue to do more examples.